Alright, let's do part 2. So we're going to be looking at a binary mixture of benzene and toluene. We're going to write a Python function for the dew temperature, dew pressure, bubble temperature, and bubble pressure. And then we're going to generate two equilibrium plots for both the curves of the bubble point and the dew point, one at constant temperature and one at constant pressure. So let's get started. First, as you can see, we imported our CHE tools and then all of our systems. And then I already put in a little array for benzene and toluene because that's the binary mixture we're using. I added our temperature and constant pressure, and then this is the mole fractions for the volume and the liquid of our binary mixture of benzene and toluene. Benzene is 0.3 and toluene 0.7. That is because they add up to 1, and as we know, it always needs to add up to 1. Let's get, not that, there we go. So let's start with the bubble pressure. Let's get rid of this one. Define it. Bubble P. That is in terms of the mole fraction of the liquid and temperature. We're going to return, as we can see from earlier, the bubble pressure is equal to the sum of the mole fraction times the saturated vapor pressure. So we want P sum of X times Perfect. Next we need to do the bubble temperature. This actually needs to be a function inside of a function because we need to specify that temperature has to be 0 at this point. So we need to return an array that the bubble pressure of X and T minus P correct. I believe that's correct. And we just need to return well, we see our function is when t equals 0. So if we're setting something to 0, then we need to use the root solver. So that's what I forgot. The root solver, our equation is going to be EQ. Our initial guess, we can do 298 kelvins. And yeah, that's all we need. Then we can pull out that last little chunk there. So let's look. Let's make sure. Let's do bubble P of so it spit us out an array. This is our pressure. This is the bubble pressure given this temperature, 393 kelvins. So if we put in our bubble temperature, if we did it right, it should spit out 393 kelvins if we put in the pressure it gave us, which is 180,963 pascals. And just like that, it spit out 393 kelvins, so that means we did that correct. Now let's move on to the dew pressure. Now that is in terms of the gaseous mole fraction of the vapor mole fraction. This is going to be very similar to up above, except you got to define it first. except this time it's going to be 1 over, no, not you, gosh dang it, I messed up my stuff. Not this one. We want this to go over here, so then we can do this. So we want 1 over the mole fraction of the vapor over the vapor pressure. So we want 1 over y divided by P dot P vap with respect to temperature. Are we good? Do I need one more? No, that's good. Very good. And then this is going to, the dew temperature is going to be almost the exact same as the dew, the bubble temperature. Just in terms of y here, it's going to be almost what just happened. Dew temperature then we need to define another equation. Make this one v again. T equals v 0 and v is 0. Return. We want to turn the dew pressure minus P. And then the same thing, we need to use the root solver. And then we can do the exact same check for this one. There we go. It should have really only spit out 1. So that's concerning. Let's look. Oh, it's because I put X. That's why. That's the problem. Still spit out 2. Interesting. Let's try it. Alright, we made a mistake. Let's figure it out, because this should only spit out 1 number. Oh, I know what it is. So, this does need to be the sum of all of the different components. I just noticed because I looked up here at this one. Notice we forgot that. There we go, perfect. Alright, now let's do the dew temperature. So that's Y, and then if we put in the pressure it gave it, which is 118,000, nope, 1,118,000, no, I can't do numbers, whatever that number is. And it spits out 393 Kelvin. So that is a good way to test that we're doing things right, and it looks like we are. So those are the 4 functions for solving the bubble point and the dew point. Now we need to look at making our equilibrium graph. So the first one we're going to start with is the temperature one. For the since temperature is constant, our y-axis is going to be pressure, and our x-axis is going to be benzene. Why is it benzene? Because benzene is the most volatile component because it has the lowest boiling point. So we need to specify some points for the x-axis. We can go from 0 to 1. So then we can go from 0 to 1, and we'll have even points, so we'll do 11. And then we also need to have toluene in there, obviously, but it's going to be the opposite of benzene, or since they both add up to 1, it's just 1 minus benzene, so that's 1 minus Z1, so they add up to 1. Then we also need to make a new y-axis, because if we just can't plug in the bubble pressure because it'll get confused, so we're going to do bubble P, we're going to make a list, bubble P list, and this is going to be Z1, just basically doing the same function up there as up there, just for the 2 components we have. So that this is just a base one for all of the components. We're just doing one for just these 2. So Z1 is benzene, Z2 is toluene. So Z1 times P dot, well actually I lied. I'm going to make one more variable. We're going to call this saturated pressure is equal to the vapor pressure with respect to temperature. So it's just basically the same thing. We're just eliminating another function. So this is going to be that times P sat, and then this is plus Z2 times P sat. What don't you like? What's the problem? Hey-o. I'm gonna copy that, get it out of here. Okay, so it was a problem with that line. Bubble P list equal to Z1 times P sat. We defined P sat already. What's the problem? We defined Z2. Interesting. Can we put this on a different line maybe? Is that what the problem is? I don't know what the problem is. I'm just troubleshooting currently. No, you see it doesn't like that either. Alright, I'm gonna think of what's wrong with this, so I'm gonna just do some other stuff here. Make subplots. We need 1 rows and 2 columns. Because we're gonna have 2 graphs. So fig dot underscore our x-axis is always going to be Z1, and then for this one our y-axis is going to be bubble P list. We want this to be row, column. Alright, I'm not going to shift enter that yet because I know it's not going to work. So I need to figure out what's the problem with our bubble. list here. Does this need to be an array? I don't think so. Can I add some code? Yeah, that's right. That is an array. I might cut all this out of the video. Taking a while here. Let's see. Is it like it just like, no, it doesn't. I'm like, what's the problem here? Alright, so I figured it out after a little deliberation here. I forgot, so when I called the vapor pressure, I needed to specify which product I was talking about, so we need to do that. So by saying PSAT of 0, that's saying the vapor pressure of benzene. So this one I need to do toluene mole fraction times vapor pressure of toluene, and that should work. And then this should work. And there is the equilibrium line at constant temperature of the bubble point. So you can see here the temperature of our graph as it increases. Now we can do the dew point. So let's add that. So we need to basically, since we have both of these arrays here, we just need to basically do the dew point function for them and then append that list. So we need to do pressure lists, make that an array, and then for what do I want to call this? I1 and Z1. No, this is Y2. Right? No. Yes. No. Y2 equals 1 minus Y1. Right? Yeah. Like. And then do see if I can remember how to do append something. That might be right, it might not be. We're gonna find out. Cross fingers. Not quite. Nope. Alright, now cross your fingers. No. Alright. Oh, let's see if I can remember. I think my append statement is incorrect. know it's a append statement. I just need to figure out, because I know I have to have this in here, because this needs to be an array. Shoot. Do we want P in here? No. Do P. Do we want to? I know I'm close too, I'm just not quite grasping it fully. Goodness. I definitely think this needs to just be the normal dp. And then we obviously have to call y and p, y and t, mole fraction of the vapor and the temperature. Oh, goodness. Let's try this. So I know it has to be an array, but maybe I have to put in array. Okay. Where'd my second graph go? Why is it not showing up? This is supposed to be temperature. That's not right. Let's look and make sure everything is good. That's good. That's good. There we go. So the problem there was I had the sum is not over the whole thing. It's just the denominators under the sum. So that's important. Anyway, there is the bubble point and the dew point equilibrium at constant temperature. So if we have a mixture of half and half, which is what this is right here. This is half benzene, which means we would have half of toluene, and we come up to the dew point graph, you would see at 180 Kelvin, the pressure to make the first bubble, or the first condensation, would be 181,000 pascals, and the first bubble would form at around 200. That's not the temperature, that's the pressure. So that would form at around 181,000 pascals and 214 pascals for the bubble. So that is at a constant temperature of 393 Kelvin. 393 Kelvin, the first at one half mixture, the first bubble would form, the first condensation of one of the, like the first condensing, the first dew pressure, the first dew would form at 181,000 pascals, and the first bubble would form at 214 pascals, 181,000 pascals. So now let's move on to the second graph, which is at constant pressure. So it's going to be somewhat similar to this up here, except we're going to need to do this for the bubble temperature. For, what do we want to call this? I guess it's going to be the same for both of them, so we just say xy1 and z1, xy2 equals 1 minus xy1 I'm just doing the same thing I did up top. Hopefully this is correct. I think it is, and then we need the not bubble, this is dew. No, this is bubble. I'm losing my absolute mind right now. Let me tell you. Losing it. Bubble. Temperature list. Bubble. Temperature list. B-U-B-B-L-E. Append. Boom. Alright. This is going to be X and P. What's the problem? Why? Why can't you do that? Why can't you do that? this is going to be almost the exact same. This is going to be the dew temperature. Let's go and bang these in here. Fig.add. Cross your fingers. Here we go. Perfect. Yes. All right. And then this graph that we just created here on the second one here is the equilibrium of the bubble point and the dew point at constant pressure. So these are temperature here. So if we have a 1/2 mixture at 380 degrees Kelvin would be the first bubble, and 385 degrees Kelvin would start dew. Would be the first dew. Would be the dew point, and that is at 150,000 pascals. That is part 2, and then next we will be deriving the Rutherford-Rice equation for an end-component flash calculation at a given temperature and pressure, and then we're going to use that equation to perform a fixed TP flash calculation for a feed of 4 moles of benzene, 6 moles of toluene with the flash drum set at 393 kelvins and 150,000 pascals. So there's that, and see you in the next one. Thank you.